Hello guys, welcome to Backbencher Studies channel. In the last video, we discussed the resonant peak of the system and how the frequency response of a second order system varies. So in this tutorial, we are learning the polar plot of a system. So the polar plot is a plot two-dimensional plot which depicts the change in magnitude and phase of the system with respect to the frequency omega, angular frequency omega, varying from 0 to infinite. So an advantage of this polar plot is that it shows both frequency response, a magnitude and phase in a single plot. So let us start our session by knowing how we can plot a polar plot for a given transfer function or for a given system. So let us start. We have to study complex numbers first. So if we have a complex number Z1 which is containing a real part of A and imaginary part of B, then the complex number Z1 can be written in terms of the magnitude and phase of the Z1, where magnitude of this complex number is square root of A square plus B square. Angle of this Z1 is tan inverse of B by A. And we similarly, if we have another complex number Z2, then corresponding magnitude and phase will be this and this. So if we want to find out the magnitude of a division of this complex numbers, then we can simply find out the division of individual complex numbers. So Z1 by Z2 magnitude would be magnitude of Z1 divided by magnitude of Z2, whereas if we have Z1 by Z2 phase, then we need to subtract the phase of Z1 with respect to phase of Z2 over here. So if we have a complex number Z1 equal to 1 plus J1 and Z2 equal to 4 plus J3, then we need to find out the magnitude of Z1 by Z2 and angle of Z1 by Z2. So we have the magnitude of Z1 as root square root of 2 and angle of Z1 as 45 degrees, and we have the magnitude of Z2 over here. We have that square root of 4 square plus 3 square equal to 5, and angle of Z1, so Z2 is nothing but 37 degrees, that is tan inverse of 3 by 4. So if we find out the magnitude, we have square root of 2 by 5 and angle of Z1 by Z2 complex number is 45 minus 37 degrees. So this is a simple introduction to complex numbers, and we can plot complex numbers in complex Z plane as well. So we have the distance from origin as the magnitude of this corresponding complex number, and the angle with respect to the positive real axis is what we call as the phase of this complex number. So this is the real line and this is the imaginary line. The angle is measured clockwise in anti-clockwise direction is positive, and the angle which is measured in clockwise direction is negative. So we have 0 degrees or 360 degrees over here in the positive real axis line, and if we are moving anti-clockwise, then we have positive 90 degrees in the anti-clockwise direction, and if we move further we have positive 180 degrees, and if we move further we have positive 270, and if we move further we have 360 degrees over here. And if we move in clockwise direction, then we have minus 90, minus 180 and minus 270 over here. So this is the convention to represent the angle of a complex number, and the distance from the origin to this point, which is the point of this complex number is what we call as the magnitude of this complex number. So we have this diagonal over here, which is having side of 1 and 1, is having the length of square root of 2, and this diagonal which is having the the angle adjacent side as 4 and opposite side as 3, then we have this corresponding length hypotenuse equal to 5. So this is how we can represent the complex numbers in complex z plane. And moving on to polar plots procedure, how we can plot the polar plot. So let us see. So we need to find out the frequency response first in order to plot the polar plot. So we need to substitute the s equal to j omega in our open loop transfer function so as to find out the frequency response of the system, and we need to find out the expression for magnitude and phase of this corresponding open loop transfer function, and we need to find out the magnitude values and phase values at omega equal to 0. So this is one point. So we need 4 points in our polar plot. So by tracking these 4 points we can plot our polar plot. First point is at omega equal to 0. We need to find out both magnitude and phase of this corresponding frequency response, and we need to find out the magnitude and phase at omega equal to infinite, and we need to write this frequency response in terms of the real parts and imaginary parts. By equating real part equal to 0, we can find out the intersection with respect to imaginary axis. So if we equate real part of z equal to 0, then what we are left with is the imaginary part of that. The intersection of that complex number or of that polar plot with respect to the imaginary axis is what we have at real part when we equate that real part to 0. And similarly, if we equate the imaginary part as 0, then we can find out the intersection with the real axis. So these 4 points are what is required to actually plot the polar plot. So by considering these 4 points, we can draw the polar plot. So let us start problems. By solving problems, you will be much more clear about this polar plot. That's it for today, guys. In the next lecture, we'll be solving a problem based on polar plot. So thank you, guys. Thank you for your amazing time.